Good morning. I am Guido Colombo. I am in charge of Orchestra, an innovative startup of the incubator of the Politecnico in Turin. We are golden exhibitor at the conference, and we are also delighted to offer you this 1-hour seminar about the experience we have coupling simulation tools with our Industry 4.0 technology for small-medium businesses. Together with me, Marco Roberti from BIESSEGROUP will drive you through this presentation. Please, Marco, present yourself.
Good morning. I am Marco Roberti. I am a software developer and analyst. I have been working in BS for 7 years. For about 3 years, I have held the position of team manager of the BeSolid platform. In particular, I deal with the CAD component, simulator component, and all the software parts for communicating with the machine. In this presentation, I will show you the feature of the suite, focusing on simulation module, that is useful for recovering machining's execution times.
We want to highlight how the computer-aided engineering software tools may give a lot of advantages when coupled with planning real-time production progress. And this tools becomes a link element between the ICT systems and the operation technology. Any product design may end with simulation of a work process. Generally, machine builders may offer specific tools to predict timing for each work phase, specifically for their machines. On the other hand, manufacturers can then, using this simulation data, they can better plan and schedule their production order using their own ERP and MES application. But how precise is the simulation and how can be accuracy good in estimating realistic times for each work phase? We have to take in consideration machine setup and work phase configuration. We have to consider any shifting of the machine efficiency over time, and all problems related to logistics and personnel who can really affect the efficiency of a production phase.
Now, let's go inside the BS world. In this presentation, I will talk about how to realistically calculate the production times of a product based on a system developed by BS. Before that, I give you a brief overview of the BS reality. BS is a business unit of the BS Group. Since 1969, it has designed, manufactured and marketed a comprehensive range of technologies and solutions for joiners and large furniture, windows, doors, and wood building components manufacturers. In recent years, he has also been active in the plastic processing machinery sector, developing ad hoc solution for a growing market. Here we can see the main BS sector: CNC work center, edge bending, automated panel handling, etc. Let's start talking about BeSolid. BeSolid is a platform developed by BS Soft, which is the software department of BS. What is BeSolid? It is a platform that offers the user all the function for managing the processes that lead to the industrialization of a product. The platform offers a solution dedicated mainly to the woodworking and advanced material processing machines sector. The focus of this solution are CNC work centers, It consists of a series of applications. The main application, BeSolid, offers an environment for the design, programming of machining, and the execution on the machine of a specific product. The platform also contains vertical applications to satisfy market requests, like BNest for nesting, BWindows for the design of fixtures, BEdge for edging, etc. Now let's enter the suite and let's see the main application, that is BeSolid. BeSolid is the center of the suite. All vertical applications of the suite interface with BeSolid. BeSolid uses various modules offered by the platform to perform its functions. The main modules are as follows. The CAD module offers all the features for CAD drawing. In this module, we can find all the functionalities for two-dimensional and three-dimensional modeling. The CAM module is the module for programming and calculating the toolpath of the machining. The preview module is useful to see the programming result quickly. CAD-CAM programming is not just the geometry and toolpath, but also contains all the operations that the machine needs to do to achieve the result. The machine programming module takes care of this. At the end of all programming, thanks to the machine simulation module, it is possible to simulate the program on the machine. Once the programs have been completed, they can be run on the machine thanks to the Workless module. Now we will do a quick overview of the modules before focusing on the module of our interest. As mentioned in the previous slide, the CAD module offers all the functions for two-dimensional and three-dimensional design. Through this module, the user can design the product he intends to produce. Alternatively, the module offers the possibility to import a wide range of CAD files. This functionality is very important when the design is done by a dedicated internal or external department. As we can see in the image, the user has designed his object in a three-dimensional way. The CAM module is very extensive. Here we briefly. During the design, the user often needs to verify that the programming is correct. This is the purpose of the preview module. Show the result based on the toolpaths calculated by the CAM. As we can see in the video, the preview makes a mini simulation of the machining based on the toolpaths. The user can adjust the speed or can request to see the result immediately. In the main side of BSuite, I said that a program is not only made up of toolpaths and geometries, but needs a series of machine operations to run on the machine. This is the scope of machine programming. Machine operations are many. Principal are the most important is the tooling of the machine work table, which must receive the piece to be machined. Piece movements during the execution of the program. This can happen when the machine has to work on either side of the piece. Activation or deactivation of the vacuum in the supports. It's also possible to program a pause to allow the operator intervention, for example for manual cleaning operation. Another important operation is the removal of scrap. This can be done manually by operator or by intervention of a dedicated robot. In the following slides, we will focus on this module. The machine simulation module has the purpose to do a realistic simulation on a 3D machine. Realism is a requirement that customers have asked us to perform the following task. The first task, calculation of project execution time. Verify that result is as expected. The third, but not the least, check that there are no collisions between the machine parts and between the non-cutting part of the tool and the pieces. The concept of realism is very important and will be described later. The Workless module has the purpose of running a list of programs on the machine. In this module, the machine simulation module is very useful because it allows the user to calculate the execution time of a work list, which we can see indicated with the green arrow. Clearly, that the time is a net of human intervention. The same concept applies to collision. The execution of a work list is interrupted if one of the programs fails the collision check. As I mentioned earlier, let's focus on the simulation module. I said earlier, the module offers a realistic simulation. Let's start by asking ourselves this question: why is the simulator realistic? First of all, being a software department within BS works out to our advantage. First, the three-dimensional kinematic model of the machine is the result of collaboration between the designers of our department and the BS technical office. So, the three-dimensional parts come from the technical drawings of the machine designs. As a consequence of previous point, all the kinematic joints of the model reflect the real machine. Each type of tool aggregate device is synchronized with the real machine, both in terms of its data and in terms of its morphology. This is a very important point. BeSolid silently starts a simulated numerical control, which is the same numerical control present on the real machine. When BeSolid simulates a program, it executes it on that numerical control, which returns the instruction for the simulation. This is important because BeSolid does not do an interpretation of the machine file, but the work is left to the real numeric control. The simulated numeric control reflects the real control in the machine. Now, let's take a look at the simulator workflow and the components involved. Let's start by analyzing input and output of simulator. In the diagram, we can see three inputs. In orange, we have the grammar entities, which are the instructions that are sent to BeSolid by the numerical control. For example, the movement of an axis, the movement of a piston, the activation of a spindle, etc. In green, another input is the document to be simulated. It contains the piece, machining, and machine operations. In blue, the three-dimensional kinematic model of the machine. In purple, the simulator output, the statements. Statements are the simulation instructions which are applied to the 3D model during the execution of the simulation. In the following slide, we will analyze every single element of input and output. Let's start with the kinematic model. That is the one of main points for the realism of the simulation. I just said that the technical department provides us the three-dimensional drawings of the machine. Our designers simplify the model by removing the parts that are not important for the purpose of collision control and the success of the simulation. Our design assemble the various parts of the machine and connecting them with kinematic constraints. For standard machines, the model creation operation is done automatically by the software. The software produces the machine model starting from the machine production list and the data of the numerical control and PLC. The joints that connect the components are different and are of different types, including prismatic joints, like a beam movement, rotative joint, like a 5-axis spindle movement, solid joins like a tool loaded in a tool holder. Another input is the BeSolid document. The BeSolid document is the result of user programming using the modules offered by BeSolid. Contains work, pieces, machine operation, and contains also equipment information like position of the panels on the plane, top equipment, jig, supports, plane, etc. Another core of realism are grammar entities. Now let's see how grammar entities are produced. Let's start with the user who requests the system to simulate a program or document. BeSolid processes that program by calculating its machining, optimizing the machining processes, and generating the machine code, ISO. In this case, ISO code. The ISO program is executed in the simulated numerical control. The numerical control is made up of various services. One of these services includes a component called BeSolid DLL, developed by us in collaboration with departments that manage the numerical control. What happens inside the BeSolid DLL component? At each cycle, the BeSolid DLL accesses position on the shared memory of NS and numeric control and PLC tables and ISO markers. It makes the appropriate change checks and populate an instruction queue shared with BSuite instruction queue. Il simulation module reads the shared queue and extrapolates the grammar entity. We can see that the grammar entity contains movement of an axis, tool activation, spindle activation, little simulation instruction. Finally, let's see the output of the simulator, which we called statement. We said that the grammar entities are instructions from the numerical control. They are simple instructions, such as, for example, the movement of machine axis, the activation of a tool, the loading of a tool, panel handling, etc. The statements are the result of the elaboration of the grammar entity by the simulator, and they are operations that act on the three-dimensional model to implement the movements of the simulation. Simple instructions contained in grammar entities can give rise to more complex statements. To do an example, suppose we receive the movement instruction of axis A1. The simulator recognizes that that axis is associated with the gripper on the machine, which is meant to clamp the workpiece. The simulator then moves the gripper but also executes the piece clamping instruction. In the next slide, we can see this part of simulation.
Thanks, Marco. Very well. And now let's see what we do in Orchestra. We like to say that we retune SMBs to play the same Industry 4.0 music sheet. And let's take a look together at this small video.
We all know it, deep down inside. The factory can seem like a complex place. Workers, suppliers, processes, tasks, maintenances, breakdowns, and some downtimes. Every single element appears to be beating to its own personal rhythm, regardless of what's happening around it. Our vision is that of a connected factory, harmonious and well-tuned. Over time, we perfected the craft of getting older machines to superbly interact with their newer counterparts. Complex? Not for us. It was all about finding the perfect tune.
Well, but now, what is our experience in the real manufacturing world? When we collect data, production data from the machines, and we compare with the simulated timing generated by CAD/CAM tools, we find very often a lot of discrepancies. There are too many unpredictable and recurring events that must be considered if we want really to estimate a production phase timing with a certain accuracy. Moreover, each machine has different controllers, programming and protocols, and machine signals must be normalized. If we take two different machines, the status of the machine in ready, work, hold, idle, and so on are not always equivalent and require additional algorithm to be normalized. As we are able to measure all the detailed work phase progress, all this information may be used to build a knowledge database. In this way, we can better plan and schedule future production according to different product ID, work phases, part programs, machines, tools, setup, logistics, and operators. On the other end, we can see how all these elements are integrated in a real-time cycle. If we start from the design, we can get simulation. From the simulation, we can have the right setup of the machine and the right timing. Then we start the production and we track the progress of the production. We get real-time information that can feed back the design in order to be more effective next time we have to produce this product on this machine for this work phase and with this type of setup of the machine itself. A typical manufacturing process starts collecting customer orders, proceeding with product design, production planning, production scheduling and control. And here is where we are able to supply one of the components of our product suite, the Minimus 4.0, specifically designed for small medium businesses. And to proceed with production progress and tracing, time measurement and balance, and here we apply the rest of our technology, which under the name Retuner allows the connectivity of any type of machinery and plants in order to connect, monitor, control, integrate and analyze any data flowing from the shop floor. And using this data we can then feed back the CAD/CAM to improve precision in simulation. Let's see how a typical small medium business in manufacturing can take advantage using our solution. Using our Minimus 4.0, a manufacturer can define or import his own production order. Each production order has one or more product. Each product has a full bill of material, and for each component of the bill of material, like the door, I have all the information that I need to use for the production of this component, including the different work phases, like a milling phase. Looking at processings, I have a list of all the work phases of my system. And if I look specifically to the milling, I can see that this phase has been planned between 1 and 1:30 p.m. and this is the actual date, actual starting date and actual ending date. And when we look at machineries and I open the machine where the milling has been done, I can check all the statuses which occurred during this work phase. And for each status I have the lasting in terms of start and ending time. Based on all these details, I can then compare all the work status, where I have also the quantity of items which has been produced for each work status, and the lasting of a specific status. With this information, we can feed back the simulation tools and be ready for a better estimation. We are now close to the end, and the conclusions are that simulation tools and CAD/CAM software tools get major benefits when coupled with real production data. This helps to better plan and simulate the lasting of each work phase. Plus, an ERP and MES can better plan and schedule production work phase if they work together with a computer-aided engineering tool able to predict work times based on each single machine knowledge. We thank you for your attention, and we hope our presentation was able to stimulate further discussion and new ideas between the audience. Here are also our contact in case are specific questions that we would be delighted to answer.